Everyone, it's a great pleasure today to have Team Weyrich from University College London. He's a professor of visual computing there, and he's going to talk to us about computational imaging for cultural heritage. Thank you for coming.
Thank you for having me. So, hello, thanks for coming. And today I'm going to give a bit of a cross-section around a topic that is very close to my heart. There's very many topics that I care about, but I tried to group the ones relating to heritage computing and heritage imaging. But before I dive right in, just to give you a bit of an idea of where I'm coming from topically. So I'm generally, yes, I'm a professor for visual computing, but my main bias is really in computer graphics and computational photography. So I worked in the past on aspects of skin appearance, trying to find mathematical models, how light interacts with soft tissue, obtaining these models also directly from measurements. I worked on point-based graphics, which is an alternative model to represent geometry and shapes. Even built a GPU for point-based graphics. Worked on image-based rendering. Appearance fabrication, which is a field where you try to create physical objects that have certain visual properties and interact with light following a digital description. So in a sense, it's the inverse of what I just said, finding digital models for real-world reflection. And last but not least, I work a lot in cultural heritage acquisition. So the link between all these things, and actually it took me a long time. Usually when people ask me, what is it that you actually do, I had a really hard time saying it. Eventually, I realized it's all got to do with digital representation of the real world. And that really what floats my boat. And I do like building hardware and tinkering around. So most of the projects involve hardware and imaging in one way or another. So this is a bit my background, and that's also how I ended up working with archaeologists in the heritage domain. And it just so happens that most people, if they hear, yes, there are some museums, memory institutions, archaeologists over there, and there's some engineers and scientists over there, and how could they actually interface, and how could one help the other, then many people, the first thing coming to their mind is 3D scanning. And this is exactly what happened. Somebody knew that I did something like 3D scanning, and there was someone with stuff that could be scanned, and they brought us together. And then I started diving into this world. And I have to say, it is much more than just 3D scanning. So digital imaging is here to stay in heritage applications. It's really, there's also finally some emerging standards, how it's best done, and so on. And any scanning or imaging is still mostly done for documentation purposes. There's the concept of a digital surrogate, saying, once you create a good enough digital representation of an object, that digital model can replace the object for certain applications in certain cases. So depending on what you'd like to study, you can also alternatively study the digital object, which has advantages if it's not if access to the object is not easy, or beware if the object might actually be damaged at some point. So this is the general idea, and it also led to a situation that many people have this very fuzzy and optimistic hope that just digitizing something, it's going to be good for something. Yeah? Surely it's help. And it involves computers, and computers can do everything better anyway. So that's the idea. And this is really how I basically got into this mess. But then it turned out there's actually very few projects out there that before they start imaging or digitizing anything, that they actually start talking to the absolute end user at the, let's say, humanities scholars, trying to understand what their research questions are and how those research questions could be answered with digital data sets. And maybe there are certain aspects that digital data set cannot reproduce. And this is basically a bit of a common theme that ran through all of my research. And today I'm going to talk about 3 examples where that is going to come up again, where we try to do things in a way that is guided by the humanities questions. So here's, again, a little bit let's say, the naive pipeline, how most people approach it. The part that's maybe not very obvious is that often before you start any imaging project, you actually have to make sure that the artifacts that you're scanning are in good shape. So that involves often physical restoration, and it's already important to interface with the people who do the physical restoration so that they understand which bits need cleaning, restoring, and so on. After that, you image or 3D scan, ideally involving lasers and other fancy things. And then we all know that we're immediately faced with this question of what exactly are we acquiring, geometry, colors, at what accuracy, and what technology are we using, and so on. And then we've got a 3D reconstruction from that. Somehow there's methods that can produce this, and maybe we end up with a triangle mesh, for instance. And then this is the critical bit. We use it somehow. You give it to someone, and they're going to be happy with it. So that's basically the generic pipeline. And this is then often the point where there is a bit of an awakening when people realize, oh, actually, we put a huge effort into something that in the end was not relevant, or we forgot to acquire something that will be relevant, and so on. If in turn you let cultural heritage questions guide this kind of system design, you immediately start getting implications on what data to exactly acquire, what are the quality requirements, which actually takes a fair bit of communication effort with the humanities. Because as engineers, we're used to what it means if somebody tells me, okay, give me the error bars. At what accuracy do you need this? If you talk to someone who isn't trained in that field, they often think, well, I don't want these errors. Why do you ask how many errors do you want? Can we have it with no error? And can you just give me the geometry? It's amazing. I had forgot how non-trivial that insight is, that thinking in terms of error bars. Usability is an aspect, because depending of, let's say, if you have a large amount of objects, then it might actually no longer feasible that the computer science professor himself does all the imaging. Maybe you have to find someone else who can put half a year aside to just do acquisition, and at that point it's a question how much training is required for technology. I already just touched at number of items, number of artifacts. At that point, scalability comes in, and all of those are things that should inform system designs. And what really excites me, where I see a really good research opportunity as well, is that once you really start looking at this in detail, you suddenly have new opportunities to create dedicated algorithms, process data, for instance, in a way that already knows the domain constraints. And we're going to see this especially in the first example now. So I'm going to talk about a project where we helped reassembling wall paintings, late Bronze Age wall paintings. I'll talk about the restoration of the so-called Great Parchment book. So many hundred pages of parchment that fell victim to a fire. And in the end, I'm going to have a bit of a goodie that has not yet been publicly announced, so I've been dancing around a little bit, and we'll get to it. Right. Let's start with the first project. So this takes place at the beautiful island of Santorini in the middle of the Aegean Sea. The island of Santorini has a peculiar shape, and that's because it's a volcano that is, it's basically just the tip of the volcano pointing out, coming out of the ocean, and you have a huge crater in the middle of the caldera that is filled with the ocean. And, is the Mediterranean Sea an ocean? I don't think it is. Correction. Right, so on that island lived also a late Bronze Age civilization, about 3,500 years ago. There's a lot of evidence of that civilization because there was trade with other Mediterranean civilizations. And there's evidence on the island of fishing and agriculture and livestock. However, much of the civilization got destroyed during a volcanic eruption. And since the late 60s, there's been an excavation on site excavating a city that was first destroyed by an earthquake preceding the eruption, and then was covered and preserved by the ashes. It's very much like Pompeii, which most people should be familiar with. The city is actually astonishingly difficult word. It's amazingly well preserved. For instance, these walls that you see here are mud brick walls This is something that normally erodes very quickly. And those are 3,500 years mud brick walls. One of the most exciting finds on this, in this city is that many interior walls of these buildings were covered in wall paintings, and many of them are actually proper frescoes. However, during the earthquake, these frescoes detached from the walls, fell onto the ground, shattered into many pieces. Often, they had multi-story buildings, actually. Late Bronze Age doesn't mean they were living in a cave. The only thing they didn't have was iron, essentially. So they had multi-story buildings that also partially collapsed, and then you had frescoes mixing from multiple stories in a single room. So this creates, if you allow the flippant language, just led to the, let's say, one of the largest jigsaw puzzles in the world. And there is an ongoing process of assembling as many of these wall paintings as possible in order also to reconstruct the iconography that is on the wall paintings. And it's a largely manual process, and it's fairly laborious. And the conservators themselves estimate that they have enough fragments of wall paintings in their storeroom that they're going to be busy for another 150 years. And mind you, there's only a small fraction of the city that's been excavated so far. The rest is left for future generations, so it's a huge find. So the whole project came to life when someone thought, can we not use computers to speed this up? Because computers are fast. Right, and that's when our team came in. At the time, it was still at Princeton University. So it was Simon Sienkiewicz and I who were approached and said, okay, yeah, we're going to do it, even though we knew. Actually, Simon took me aside at the time and said, I was still a postdoc, and he said, look, as a piece of career advice, I have to advise you against it. It's doing it. It's such a nightmarish project. In your situation, you should write a lot of papers, and you shouldn't take on such tasks. But I thought, it's the kind of stuff why I became an engineer and why I went into computer graphics, and this might be the once in a lifetime opportunity. I'm not going to pass on it. That's why we went into it. So the other interesting thing about the project is that it's been then going on for a long time. So people traveled all over the world and ended up in different places. And this is where we are now. So we started back then by saying we have to study the actual process that people are using at the moment. This really goes back to before you walk in as the engineer and come up with all the solutions, you should first understand how other people are doing it. So we started with a graduate student seminar. One of the graduate students involved was actually Diego Nehab. Very glad you're here. And we looked into plaster, into how to paint frescoes onto plaster. This is a very young me. And we even simulated earthquakes and tried to create fractures in frescoes. We even had the conservators on site create a fake fresco for us. They also made quite some effort. They created it in the same fashion as the original frescoes. They painted them with typical iconography, then they shattered into pieces, then they threw part of the pieces away, because that's also realistic. You never find all the pieces. So I threw some of it away, dug it into the ground, original Santorini ground, dug it up again, and shipped it to us. So this was the data set that we spent a significant amount of time on. But then we felt we have to go on site, and here is proof. And talk to the conservators there. I did essentially this kind of requirements analysis that for some reason is standard if you're basically in the business of selling technical solutions to other technically minded people. But for some reason, there's too many projects out there that have, when engineers and heritage people interface, that don't really go through this requirement analysis. And if I may offer a theory where that might be, it's because it's one of the most difficult communication tasks, especially if people come from completely different backgrounds in their training, in their understanding what science is, what research is. It's easily said to say, oh yes, there are some research questions, but the people in the room don't even have remotely the same notion of what is a research question, what's a valid question, what is publishable, for instance. So we went through that effort, we talked to them, learned about the existing process, proposed already some solutions that we had developed in the grad seminar, and we realized very, very quickly that usability is going to be key, because at the end of the day, they would have to use the system, and it couldn't be us. And it has to integrate into an existing workflow. You know? So you cannot just walk into an existing operation and just say, all right, we're now telling you to do everything differently, and expect that they take on that huge risk. So we learned that the organization was, okay, there was still a lot of naivety on our side. So somehow we assumed there's going to be a database somewhere. We assumed that the individual fragments are going to be labeled, but that's not the case. They were organized in trays, roughly by their find. The documentation was handwritten, obviously Greek handwriting in little notebooks. Because, I mean, this is not surprising if you think about it, because the actual task of assembling, it's not obvious what benefit would come out of someone trying to describe an individual fragment. On some level, they wouldn't even consider that individual fragment as the artifact. The artifact is the assembled, restored object, so that's what they're focusing on. And there's also the question, are you just going to spend decades hand-labeling things, or are you spending some time assembling? The assembly also required cleaning and stabilizing beforehand, so that during handling things wouldn't fall apart. But then the most significant situation, the most significant challenge, is the sheer number of fragments. So some of these fragments, they may be maybe 2 or 3 centimeters long, sometimes less, sometimes more. And it's just huge amounts of fragments, and they had many of them, at least the active set, basically, the set that they're currently, at any point in time, assembling is lying on tables in their lab. And then they sequentially try out pairs, pairwise matches. But you cannot just put two together and say, okay, it's a match. It's not a match. You have to start trying every possible orientation and rotation against them. So it's a very laborious thing. And the test whether something matches is whether the 3D edge profiles correspond to the point that if you put them together, that you can feel that nothing wiggles anymore. It's we tried it ourselves. There's lots of situations where you think, oh, this could be a match, but if you do actually find a real match, it has this really satisfying feeling. You put them together and it just locks and it stays in place. So that's pretty much the methodology. However, it's not feasible in this manual process to try every possible pair. I don't have to tell you guys something about complexity if you try everything with it and so on. So what isn't a good idea for computers is certainly not a good idea if humans are involved. So what the conservators do is they try to identify fragments where it's likely that it might be a match. And for that, they use a set of criteria, for instance, thickness, because the frescoes themselves, the front surface is very, very flat, very even, but the mud brick walls that they were attached to, they were undulating. That means at different places, the frescoes had different thicknesses. But it also means that neighboring fragments should have the same or compatible thickness. That's, for instance, a very powerful criterion by which you can pretty much rule out the two pieces go together. There's exceptions, but by and large. There's other criteria, let's say the level of erosion that something received. There is the level of discoloration and fading, pigments involved in a composition, curvature. I just said that they're flat, but if you're getting close to corners of a room, it's actually really difficult to flatten the plaster without pushing some of the plaster into the corner and creating a slight curvature there. So that's another indication. And there's various criteria, and the conservators basically say that all of those collectively inform which sets of fragments are going to compare against each other. So that was basically the key set of criteria that we said should inform what we're going to acquire. Because the problem is, 3D scanning itself, yes, may be a solved problem. And anyone can 3D scan one of these little pieces, provided they've got 20 minutes time to rotate this somewhere, point it to a scanner to acquire another range map, and so on, and then using some software where you have to pre-align these things, then run ICP and register and clean the data and so on. So anyone who's ever done it knows that 3D scanning involves a lot of manual processes. So this is something that wouldn't have been feasible for thousands of fragments. So the trick was now basically, can we identify a hard subset of aspects to acquire that correspond to these criteria that the conservators care about? And it turns out you can pretty much simplify it to say, as long as the geometry itself is about 1/4 millimeter resolution, you're good. If the color reproduction, you care about color, but you only care about color at the front, at the painted surface. Yeah? And you also care a little bit about fine surface detail, let's say little traces from flattening the plaster or incisions that they used at guidelines and these kinds of things. And so yeah, 1/4 millimeter resolution, high resolution color, and structure of the surface, which you can model as a normal map. So it turns out there was a good sweet spot in terms of how to acquire these things. We found a comparatively cheap laser scanner that met the geometric requirements, that had very poor color reproduction and very low resolution color. So we decided to just use it for the 3D geometry part. But then we exploited the fact that where we actually want to know high quality color is actually just on these flat surfaces. And it turns out there are very cheap, very high quality devices that you can buy in a shop that scan 2D surfaces at high resolution color. This is one of them. So yes, we switched to flatbed scanners to acquire the color textures. And it turns out you can also use a flatbed scanner to reconstruct the surface structure. That is because in every flatbed scanner, you have a linear camera, essentially, linear CCD array, and you've got a light source to illuminate the document that you try to scan from below. Now, those two cannot be in the same position because either would block the other one, so they need to be slightly offset with respect to each other. But that also means that this imager sees every surface point illuminated under a slight angle. So the light always comes from a slight angle. So the trick that we used then was basically we scan each fragment 4 times, each time rotating it by 90 degrees. And if we register these images with each other, we have 4 corresponding images of the same surface, each time illuminated from a different direction. And so we were able to generate a photometric stereo formulation for these linear light sources that gave us pretty high quality normal maps. And we did additional tricks. We had a bit of an unusual setup of the 3D scanner. We tilted it by 90 degrees. We exploited, I'll get to that in a second. So it's basically for the specific fragment geometry that allowed us to basically in one go just scan an entire hemisphere, and then we only had to turn it over and scan the other hemisphere, rather than, as you would normally do, scan a cylindrical set of range maps and then having to fill remaining gaps. Also, our scanner software works completely automatically. So you place the fragment on there, you press a button, and it automatically, in a preview scan, finds the fragment, determines a bounding box, scans it, saves it under a running serial number. So no more clicking preview scan, bounding box selection, save dialog, et cetera, how you would normally do these things. So yeah, okay, this isn't rocket science, but it turns out those little bits make a huge difference between a theoretical possibility and a system that you can actually use in the field. And we used also some custom registration algorithms that exploit the fact that the fragments are flat on one side. that actually gave a lot of stability to the system. And the system ended up being so stable because of all these special algorithms specialized for the fragments, that only about 2% of the fragments had errors. And we decided, instead of then providing a complex user interface to fix these things, if it's only 2%, the right answer is do it again. And that was, in terms of technical workflow, something that would also fit much better into the day-to-day operations. So it had a high usability. It was very well accepted by the conservation team, required minimum user interaction, and so far everyone whom we trained in the system didn't take more than 30 minutes for training. And after that, people were able to basically create complete data sets for fragments at a rate of about 6 minutes per fragment, which was good, and the system is scalable. What I'm not going to talk about today are then our algorithms that we use to find matches. So we made quite some progress there as well, and also learned our respect of how hard these jigsaw problems are. And I'm only going to say as much. The two difficulties in that assembly problem are that that you don't have full certainty whether something is a match or not. You can say this with a 90% likelihood this might be a match or not. And that basically leads to a search problem. And the other thing is that you always have a little bit error on your 3D scans. So that means as you start putting multiple fragments together and you build chains of them, there's some error propagation taking place. That means if you close a loop of multiple pieces connected with each other, that loop may no longer close. So you need to allow for some wiggle room. But the moment you allow for wiggle room, you can, at some point, as the size of your fresco grows, you end up in a situation that you can always fit even an incorrect match. You can somewhat fit it in there, and the wiggle room is going to make it fit. So it's these kinds of this match finding in the presence of high uncertainty that ended up being an interesting problem. Right. But again, this talk was meant to focusing on basically how do you design a system that is fit for a very specific purpose in the heritage domain, and that's why I'm not going to go further into this. So the key was really to only acquire the data that was relevant, and specifically for matching, not relevant for possible other applications that somebody might have. And that we basically did not just design a couple of algorithms, but the entire workflow, the hardware, everything out of one hand. And that also requires then basically, or allows you to balance levels of automation against user interaction. And lastly, I should say, the moment you do this, you can go with low-cost solutions as well. And that by itself allows for scalability. I was planning to take some questions at the end, if that's okay, right? And would go into the next project. So this kind of approach of trying to build custom systems for heritage imaging problems, that really ended up as being something that fascinated me greatly, and so I rushed into the next project. And in this case, it was a collaboration with the London Metropolitan Archives. And they had a very precious artifact. They had a doomsday book from Northern Ireland. So the term doomsday book basically specifies an administrative document in which you have basically a complete description of a current state of ownership, who owns which lands, who inherited what by whom, who owes money to whom, or who works for whom, and all these kinds of things. So this manuscript is a doomsday book from the region of Londonderry. It's a region in today's Northern Ireland. And what makes this particularly interesting is it's from a time, and it's basically a snapshot. Normally these administrative documents aren't very exciting, but it's a snapshot of property relationships in Northern Ireland just before the English crown invaded and changed everything. So that makes it almost a bit of a political document, obviously. So this very valuable document was around, but then fell victim to a fire in the 18th century. And the thing that, yes, and it was so heavily damaged that access was restricted to the point that even historians were not allowed to study the book. So the information in the book was essentially lost. So what happens to parchment when it is exposed to heat? And this parchment was actually inside a wooden box that was in a burning library, which is unfortunately something that at the time happened very often because, you know, libraries are full with flammable things, and you also need light for reading, and light is fire, and yeah, there's been many libraries that burned over the centuries. And during that burning library, the book was enclosed in a wooden box, got heated almost to burning point, but parchment doesn't burn as easily as paper because it's a different product. It's animal hide. And so it does the same that, for instance, hair does if you get close to a candle. It starts curling and deforming and shriveling rather than just burning up. There's also some chemical changes taking place. And after that, the parchment is very brittle and very difficult to handle. So this box is an image of, it's one of the boxes where the remnants of the parchment book were held. And they colloquially, internally, sometimes called it the poppadom manuscript, because not only does it look with its like Indian poppadoms, also when you put them on the table, it has a similar sound to it. So very delicate, close to the public. So the idea was now, can we develop an imaging and restoration, digital restoration procedure that can allow us to read the contents again? You have to be always specific. You're not saying, okay, can we just restore the parchment? You'll never be able to restore it to its precise original state. So you have to find out what is it you'd like to restore. Yeah, so let's look at this kind of pipeline we looked at earlier. You can start with physical restoration. That has to be done always. Then you image, then they'll 3D reconstruct, and you use it somehow. So in this particular case, what would use it somehow be? Well, we could think, for instance, about flattening it digitally. So that was one idea. And that was already the idea that we walked in to our first meeting with London Metropolitan Archives to pitch some ideas and propose things. And so we did some requirement analysis. And the first thing that they really told us is the main thing, and really the only thing that they care about, is being able to read the text, because it's all about the content. Well, this whole idea of flattening it, they considered a lesser requirement, not so important. And then there were all the things that I wanted to do, like super color-calibrated spectral reconstructions of the contents, finding out, what the level of sheen that is on the surface of the parchment, so that we can maybe restage the parchment in its original glory in virtual reality and render it with realistic highlights and all these kinds of things. And they kept on saying, no, that's not interesting, because it's also not a very beautiful manuscript. It's an administrative document. So, yeah, I was very disappointed. Then I said, yeah, what about spectral ink analysis? We could find out, whether they use different inks. I said, well, around that time, plus minus a century, everyone in Europe was using the same ink. There's just nothing there to build. And I thought, oh, it could be a palimpsest, right? So we could find out whether someone scraped off an older text and then wrote this on top because they had to save parchment. And then they said, well, no, look, this is Northern Ireland, right? If you run out of parchment, you get another sheep. So whatever I tried, they always found a reason why the imaging methodology I wanted to apply is just not needed. And it was good, it was healthy, because in the end, I would say it was the only reason this project had a fast success, because it allowed us to focus on the absolute relevant. So the way they phrased it in the end, they said, look, even if you reconstructed something that looks like a 200 dpi fax of the original, we're happy, because we can translate it, we can read it. So the physical restoration that had to begin involves humidifying the parchments. In the past conservators of the last century have done a lot of damage to parchments by humidifying them and then trying to squish them flat. problem is much of the distortions are so severe that the parchment will still rupture and rip in the process of that. And the other thing is the chemical changes. It's a gelatinization that takes place when parchment heats, which means the whole parchment becomes more amorphous, and if you then humidify it and squish it, it's basically, it's like jelly. Huh? So LMA actually developed a method because we were working together already at that point, and so it was clear that their goal was not necessarily to create flat pages. If we could help digitally, then there was no need to do that. So the only thing we needed is that parchment was, let's say, opened up or flattens just to the degree that an imaging device can see all the surface points. Yeah? So basically, if there was a valley or a crease where something is crumbled, shriveled to the point that you cannot even look inside it, then we cannot scan it or we cannot image it. So that was basically what we told them, open it up just to the point that we can see the content. And so they developed a method that involved humidifying, padding with pads from underneath. So instead of flattening it, they rather would open it up, let it bulge, because that was a more gentle way to get rid of these creases, and we could see all the contents. And after they've done that, we started with digital restoration. So let's talk about imaging. I like lasers, so we really wanted to do laser scanning and so on. And then at some point, somebody said, "Oh, aren't you sure that photogrammetry isn't going to work? Structure from motion, these kinds of things." We said, "Nah, sure, it's not going to work." And so, but what if that guy is right? We should. Because photogrammetry is so much easier in the acquisition than what we meant to build. So we said, okay, let's try it out so we can rule it out. But it turns out it works extremely beautifully on parchment because parchment has so much surface texture. If you take, as it's seen here, a 20 megapixel digital SLR and take lots and lots of photographs, it even allows you to swap lenses in between or get closer or farther away. You can acquire within a short amount of time a lot of images of a given parchment. In this case, it's about 60 images of the same parchment, and just use structure from motion for 3D reconstruction. I've seen, or nowadays people call it photogrammetry. I've seen photogrammetry fail spectacularly on various objects, but it just turned out it works beautifully well on parchment. So, lucky us. This is a 3D reconstruction coming from the process, and this is if we texture it with the high-resolution raw images we're getting from the camera. So we've built a textured 3D data set, job done, isn't it? Well, we wanted to see whether we can flatten it. So in computer graphics, there are various techniques to flatten geometry. And they're all somewhat related to 2D texturing or finding texture coordinates of a 3D object. So who in the room is not familiar with texture parameterizations on a surface? Everyone is familiar. That is an unusual, no? Okay, I thought that would have been a very unusual audience. So the thing is basically often if you have a computer game, you've got a game character, it's got its own geometry, and you've got some colors that you would like to see on that geometry. These colors are stored in a rectangular texture, like a pixel image. And now you have to basically tell your GPU how to get that image onto the surface. So what you can do is at each vertex or at each point in your geometry, you just store a U and V coordinate that points back into this texture image and tells you how is that going to be mapped onto the surface. Yeah? Right, and if you think about it, it's actually impossible to just totally wrap an image onto an object and not see distortions. So there's a lot of research on how to find stretch minimal and distortion minimal mappings between a general shape and a surface. So that's established knowledge in computer graphics. So we felt, right, let's just use that. Let's use a minimum stretch parameterization, and this problem of optimally mapping a texture onto a geometry is the same as trying to say, let's let's optimally map an A4 page onto a parchment, right? It's clear that's the same problem. Well, it turns out if you apply these stretch minimal approaches, you get something that looks like that. Now, mind you, what you're looking at here is actually flat, even if it doesn't look like it, because the colors that you see, they still have the shading baked in of the parchment at the time when we imaged it. But the distortions are the ones that happen if you were to stretch minimally map this geometry into a plane. So if you look closely what happens, you will see that in some regions, suddenly the text becomes very, very small. And there's other regions where, because the underlying undulations were so heavy, where everything gets distorted in irregular ways. And most importantly, these kind of distortions, they're differently in different places. The reason for that is that parchment doesn't really basically deform like a rubber sheet when it's heated. It does it in very irregular ways. So, what can we do? Let's take a step back. The problem is, I just related it to texture mapping, but it's also equally related, for instance, to map making. And there is centuries of traditions of how to map a non-flat geometry onto a plane, that geometry being the Earth. And so how to map the globe onto a plane. And what is, let's say, the 21st century variant of mapping the globe onto a plane? I guess it's still called Google Earth. And the way that, or Google Maps or whatever, the way Google Earth, for instance, works is that it doesn't actually flatten the globe. What it does, it gives you basically a virtual camera with which you can fly over the globe. And as you zoom in and out, the camera's perspective, together with the underlying 3D geometry of the globe, does the mapping for you, in a sense. Yeah? And that's how you have these seamless transitions also. If you zoom in very closely, that corresponds to flying very close over the surface. At that point, your imaging is pretty much stretch minimal. And as you zoom out, the spherical nature becomes more and more apparent. So we figured we can do exactly the same for parchments. So we have a virtual camera that flies over a parchment. You can get closer, you can get further away. And at all times, you display on a screen what that virtual camera would see. And that allows you to travel over the surface, over the irregularly shaped surface of the parchment, and read it on your 2D screen. You can do additional tricks such that whenever the camera stops, you can cut out a small region around the viewport of the screen and undistort that one. Now, locally undistorting something in a stretch minimal way is a much better posed problem than this global unwarping that I showed you. And so basically the weird distortions that you expect are really minimized here. And if you look at this from the perspective of the camera, it looks like that. So it looks like we totally sidestepped the problem and replaced it with a user interface. And the transcriber, when she saw this, she was absolutely excited because she says this is already very, very close how she would transcribe other documents. You take the documents and you just move it in front of your eye in order to look around corners and read the text. However, there's still then some if you now start playing around in the viewer, you may come across things like this, for instance, right? This doesn't really look like some writing. It looks a little bit weird. And if you know a little bit about, let's say, 3D reconstruction pipelines and so on, your very first suspicion here is that it's an artifact of the, it's not really not in the original, it's an artifact of the processing. Well, this always being a possibility, the system also supports, the system knows for every part of the surface which of the original raw images contributed to it and what camera views they corresponded to. So we can pick the nearest original photograph, nearest to the current virtual view, and put this next to it. And it turns out it does look that weird. It's not a processing artifact. And there's other cases when you may have a suspicion that you lost detail. It looks suspiciously blurred in here. And if you look to a raw input photograph, you actually see that there is additional content. So that was another very important aspect of the software, that we always give the transcriber a possibility to go back to as close as possible to the real artifact. In that case, it's the initial photograph taken, in order to answer unknowns in the transcription process. Right, so we took digital flattening and replaced it by interactive viewing. And that led to a transcription. So, nice example how staying focused on the actual task at hand saved you a lot of trouble. Now, having said that, we were so successful and so fast with it that we still had some time on our hands. The students still had to graduate with something more sizable afterwards. So we thought we'll give it a stop anyway and try flattening. Okay, it turns out the biggest problem with the flattening is this irregular distortion, that some regions of the parchment distort more than others. And that's because it's this natural product. It's animal hide, and it just responds differently in different places. There are, however, cues on the parchment itself that help us reverse engineering, essentially, these distortions. And key cues are, for instance, that the lines of the book were actually fairly straight. In fact, people used guidelines when writing this document. So we built a system that allows you to trace these lines. We also built a very simple optical character recognition only for those characters that are very repeatable in the handwriting, things like, for instance, a lowercase a. If we find all the lowercase a characters on a page, we can basically infer how the font size changed due to the distortion. And we can use all of that information to reconstruct a distortion field that tells us how basically the area of at each surface point changed between the original document and the damaged version. We can further annotate this automatically extracted basically font size reconstruction in the system to have more samples of font size across the page, and we can interactively trace lines, which has to be interactive because there are so many aspects like these swashes here in the handwriting that can throw off an automatic line detection. And so with this system, it takes about 3 to 5 minutes per page to annotate a page like that. And from these annotations, we can extract a dense distortion field. And now we can undistort these pages in a way that is energy minimal, considering this distortion field that we reconstructed. Right? So, luckily we had some more time. We were able to do that as well. It has its benefits because for archival purposes, it's difficult to archive an interactive viewer. Now we're able to turn each page into a higher resolution JPEG, and that's going to survive for longer. Right, so it is again something that capitalized on a lightweight acquisition procedure. I haven't even told you that I think it's 600 pages, so 300 folios that were scanned. And we acquired just the information that we needed, and we had both a specialized viewer as well as this flattening approach. So in summary, we talked about 3 projects that demonstrated what is possible if you actually find out what exactly you'd like to image. No, not what exactly we'd like to image, but what are the people going to do with the data sets afterwards, and what are the questions that they may have. And once you really start honing in just on those questions, rather than trying to create an everlasting, holistic reproduction of the artifact, it suddenly allows for technical solutions and bespoke systems that make the impossible possible. Right? It'd be impossible to create super accurate surround reconstructions of every little piece of a fresco in any acceptable time. But if you do it in a way that you capture just what you need, it's becoming possible. And the reason that this is a challenge to begin with is that you're really operating in a large design space. You have to think about, You have to think about the, how many artifacts do you have? What's the volume of your acquisition problem? Cost is always a problem. Time, interestingly, time to a lesser degree, because somehow the heritage domain is an area where people, yes, nobody has money, but many people are continuing anyway because they do it for a good cause. So there is, it's very different to other domains to operate in. Then the complexity of your solution needs to be manageable. You have to think about how to train users for the system, what kind of type of data to acquire, and what accuracy to obtain. And the best practice how to approach this is really object dependent, and not only regarding the research question. So where I would like to take this, and I hope I find more people who would like to go behind that bandwagon, is at some point we have to stop building a completely bespoke system every time we've got an heritage problem, an imaging problem. So what I'm trying to find out, what would be good boundaries along which we can modularize solutions so that people can build their own bespoke system without doing everything from first principles. And over the last 3 years, 4 years, there's been a lot of motion in the whole photogrammetry space. So there is now photogrammetry software that finally is being used by people who don't have much experience with any other imaging methodology. So for this specific piece of technology, it turned out there was a big enough market, there was enough interest, and the problem was also confined enough that you have industrial off-the-shelf solutions for this. But there's many other aspects, especially once you get into active elimination and then processing data sets based on what you know about the elimination. That's where I would say it's still in the realm of researchers building demonstrators and proof of concept. So this is something where I believe we really need to move more in the direction of modular solution. But we also have to always think about training. We have to not only provide these modules, we also have to show people how to use them, basically. Because we're dealing with a user domain that may have a couple of inspired computer science hobbyists, but by and large, if you want to make a difference, you have to do it in a way that you can train people in how to use your systems. And obviously, it's better if those designs are open access, because then people can really build upon them. Right. So let me end on the last note, which is none of these projects would have been possible without many, many people helping and being involved. And this, maybe the number of people here on this slide should once again just underline that continuing to build completely bespoke systems is not scalable. Well, I think I will continue doing that and be it to just basically show the potential behind it, but I think we have to do better. We need modular solutions. So thank you very much. And and at that point, I'm open to questions.
Okay, thank you very much. Any questions or comments? No? Well, I do have some questions. Mm-hmm. So one of the takeaways here is that maybe the more important thing is to give a user interface to whatever digital copy you have produced, instead of trying to make a very good, precise copy of whatever you.
It is one of the ways. I think in the end you need a combination of, okay, I'm not arguing against doing it right and doing it proper and making sure that you acquire things cleanly and that you have good algorithms and so on. All of that is important. But you have to, in this kind of design space of all the options that you have, about the things that you care about, there'll always be failure cases, basically. So if you have a system that should, let's say, flatten parchments, and you go about it in an ad hoc way, then you might be able to flatten 40 or 50% of that, and that's maybe commendable, but the person who would like to read the remaining 50% says it's not good enough. Mm-hmm. If you then try to say, okay, I'll just work harder on my algorithm, you might be working on it for 15 years. And again, the person at the other end is going to be unhappy. Right. So where I'm basically bringing, I'm not saying, we should basically replace hard work with user interfaces. I'm just saying, you have to go for the biggest bang for the buck, basically. you have to find out what also really in this kind of multi-dimensional design space, which bits bring me closer to a complete success. And that's something we easily forget, that it's, especially if we like, let's say, geometry, computational geometry and these kinds of things, it's easy to forget that there is other things like user interactions, like going back and saying, well, if we acquire the data in a slightly different way, then certain cases will just not appear, right? Mm-hmm. I mean, okay. Let me just, at that point, do a slight digression, just give you a little bit more explanation of what we meant when we said, custom processing in the Fresco project.
Yes.
So, for instance, one thing that we did is, most of you are probably familiar with iterative closest point alignment, yeah? So, iterative closest point is basically you take two range maps and you bring them into correspondence by sliding them basically on top of each other. But one of the problems is that if you have flat and even surfaces, ICP tends to drift. And people address this then when they bring lots and lots of range maps together, that they run some global optimization, and that might work or might not work at some point, because the more range maps you throw in, the more degrees of freedom you have, how each of them wiggles, and yeah. So what we did in this project is we said every data set is acquired on a turntable that is motorized and turns by 60 degrees, or whatever the degree is, right? A fixed step size. Always around the same axis and at a high precision. So if you assume that that's precise enough, then registering all these range maps together doesn't really mean you need, for 10 range maps, that you need 10 times 6 degrees of freedom. All that you actually need is you have to reconstruct where in space is the axis of rotation. Yeah? And that basically cuts down the degrees of freedom tremendously, and with that, the whole optimization problem becomes much more stable. The other thing is basically, well, then you have only one hemispherical reconstruction, basically, of a fragment. So you can turn the fragment over, you do it again, you've got two such hemispheres, and that's what we actually do. But now, with traditional processing, you would end up in this kind of ill-posed problem of having these two half-complete reconstructions that might only overlap a little bit at the joint fracture line. And getting that properly aligned is, again, very, very difficult problem. At that point, you bring in that the fresco fragments are actually flat on one side, which means in the scan where the fragment is face up, you can actually detect that plane in the data set. You can just go through your range map and just find that plane. It's fairly accurate. The other scan, the fragment was face down on the turntable. Well, but that means you still know exactly where that plane is, because that plane coincides, that fresco's front face plane coincides with the plane of the turntable, which you also see in your scans. So, which means that you have now two somewhat hemispherical 3D scans, and you can register them into the same plane, which means now registering these two halves together, it becomes a 2D registration problem, 3 degrees of freedom. And those were the specific steps that made this scan processing pipeline much, much, much more stable than anything else. Yeah? So yeah, it's not just about sidestepping a problem with a user interface. We've done a little bit more of that in the second project. It can also be what can we basically tie down on right at the beginning in the workflow, at the acquisition time, that allows us to write more specific algorithms.
Thank you. So any other questions or comments? Oh, I still have another question. So, so on the painting, the last one you showed, can you use the data you recovered to help people plan the lighting when this is going to be exhibited?
I think we could. Sorry, I can't go further into this, but it's yes, no, that's a definite possibility. Yeah. Yeah.
Okay. So, if there are no more questions, let's take Tim. Thank you very much.
Okay, thank you.